We should have taken a break. It's all four. Okay. When it comes to DNA, you know, all of us heard of this thing called DNA. It was such a big fuss, I think, 5 years ago, because they were supposed to sequence the genome, right? And so it's $50 billion project, this is that, it's going to take 20 years. Nowadays, with the modern computers, you can sequence them in 3 days for the whole genome. It's crazy. I don't know if you guys watched this commercial from University of Berkeley. One of the students, I think, or the researcher, he talks about it, like, oh, I can do this, I can do this. Crazy. But anyhow. And how much would it cost to sequence it now? A couple of $1,000 from billions of dollars. It's crazy where things are heading. Okay, so let's talk about nucleic acid. Nucleic acid. Nucleic acid, see, by definition, let's just say, why would something called be acid? First of all, okay, even though it's just for you to understand, it's not necessarily important for step one, but these tiny little things matters, because if you understand, it will make your life easier. Acid, anything that donates a proton. Proton is positive hydrogen ion. Anything that donates a proton is known as acid. Anything. And the functional group of acid would be, just like an amino acid should have, carboxylic acid group, this. This is what literally acid means. In terms of function, a molecule which donates a hydrogen ion, especially if you put it in water. It dissolves in water very rapidly. So acids are highly soluble, very soluble. For that reason, they can cause reaction, they can break things. So if they donate a proton to something else and something else accepts it, the base, the composition changes. Okay, so by definition, this is what acid means. But when we use the term nucleus or nucleic acid, wow, I'm missing a C. Okay, you add the C. That means this acid is located or found where? In the nucleus. You have too many types of acid or acidic molecules, a lot. But the acidic molecule we're going to talk about now are called nucleic acid because they're found where? In the nucleus. And we're done. Life is very simple that way. There's only two types of acid that we're concerned with that are found in the nucleus, DNA and RNA. The two of them are called as a group nucleic acid, DNA and RNA. DNA and RNA. Okay, so they are nucleic acid. Okay, DNA and RNA. Let's compare these two. Since we're talking about them, let's compare them. See what are they? For example, you know, I don't know if this helps. Back in, not in my time, but at least in my parents' time, if they were gonna, because the society were closed and they're small when they want to get married, and they will say, oh, you know what, this person's daughters is so beautiful, this person's son is so beautiful, and then they had no chance of meeting, so they'll describe them. So what do they look like? When it comes to medicine, looks are the most important things. And looks meaning anatomy. Anatomy. Things that you can see with your eyes, gross anatomy. Things that you cannot see with your eyes, microanatomy or histology, same thing. So let's go over histology. You have to first of all know, what does DNA look like? Those of you who are thinking about marriage, like, yeah, I want to see some pictures. Yeah. Okay. Now, nucleic acid, number one, you have to know the structure of nucleic acid. You have to know what it looks like. At least a representation of this, right? Okay, let's do that. Now, the first thing you want to do is to see what are they made of. What are components of nucleic acid? All nucleic acid are made of nucleotides. All nucleic acids are made of nucleotides. They're made of something called nucleotides. You know, I don't like usually like selective, one narrow-minded lectures. I bring a lot of things together, even though it has nothing to do with today's lecture. Now, if you remember, we will start metabolism soon as well. We talked about major 4 macromolecules. 4 macromolecules on which your life depends. For nutrition, for survival, for production, for so forth. Can you remind me the name of those macromolecules? Carbohydrate, protein, lipids, nucleic acid. Let me ask you this. What is the building block of protein? Amino acid, amino acid, amino acid. That means, and when you say macromolecule, meaning it's a large molecule. All 4 macromolecules are polymers. Polymers. Let me write down that for you. Terminology doesn't matter. Polymers. Polymer means a large molecule that's made of multiple similar things. For example, if it's made of amino acid, the entire protein is made of multiple amino acid. So the building block of a protein is amino acid. So it's made of the same thing repeated many, many times. So if you attach amino acid in a linear chain of 3,000 amino acids, you get a hemoglobin protein, for example, or insulin protein, or lactase enzyme. At the end of the day, all proteins are made of amino acids. The arrangement might be different. The arrangement of amino acid might be different, but at the end of the day, they're all made of what? Amino acids. So that's a polymer of amino acid. A protein is what? A polymer of amino acid. A polymer of amino acid. Okay. So when we talk about DNA or RNA or nucleic acid, they're only made of nucleotides. If they're made of nucleotides, that means nucleotides must have to be, repeated over and over and over and attached in a linear fashion. So nucleic acid is a polymer of nucleotide. It is a polymer of nucleotides. Okay? For example, let's say DNA, this is nucleotides 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, few thousand, let's say. And they're all attached. Whoa, I'm erasing it. I didn't get that. They're all attached, just like beads on a string. Pearls. The beautiful pearls in a string. You can wear them. So this is a polymer. This is DNA. This is RNA. This is nucleic acid. But each single unit is called nucleotide. RNA is made of nucleotides. DNA is made of nucleotides. For example, chromosome 21 might be made of like millions of nucleotides. I don't know the exact number, but okay. All right. So when we talk about anatomy of DNA or RNA or nucleic acid, let's start with the basic building block of nucleic acid, and that is nucleotide. Okay. Now, a nucleotide is made of sugar, phosphate, what's the third one? Nitrogen base. Very good. Okay. So nucleotide itself is made of 3 components. In itself, it's made of 3 components, each nucleotide. But now, the possible nucleotides, there are total 5 possible nucleotides. There's total of 5 possible nucleotides that are part of nucleic acid. Okay, there's other nucleotides that are not part of nucleic acid, so we're not going to worry about them. We're talking about nucleic acid. It's made of adenine. We'll use for now A. What's the next letter alphabetically? C. Cytosine. Excellent. Guanine. Thymine. Uracil. I'm not a cell. I am a cell. You're right. A collection of cells. Yeah. Okay, I'm glad you're sitting in the front. Did you kick somebody out of here?
No, I dragged them.
You dragged them. Yeah. Mm. My favorite student should be sitting here, not you. I don't know where she is now, but we'll worry about her later. She's hiding behind you. Okay, now Nina's going to say everybody's your favorite student. Okay, so 1, 2, 3, 4, 5. 4 possible nucleotides. That's all. Easy to remember. Easy to remember. So now let's talk about nucleotide in terms of structure. Based on names, you're okay. It's made of 3 components: phosphate, sugar, nitrogen base. And let's make the sugar equal. It's always a ribose sugar. Ribose sugar, which is a 5-carbon sugar. 5-carbon sugar. Okay? For example, if you when you're getting married or something and then say, oh, I have this beautiful girl for you, or the beautiful young guy for you, you tell your daughter or whatever, you guys don't have it, I do. So, and then if she asks me how many hands or how many feet or how many arms or limbs they have, that's what we're talking about. Okay? Just to compare. So make sure, the parts of a nucleotide are 3. Ribose sugar, phosphate, nitrogen base. Okay? Let's look at, and we're going to do sugar metabolism after nucleotides, after DNA and genetics, and you will come to that. How do we make that? There's a pathway that generates this ribose sugar. And it's huge, 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 huge on the exam. So ribose should look like that. It's a 5-carbon sugar. So the shape of it should be pentagon. Oxygen is not part of it. So going clockwise from oxygen, you would say this is carbon 1, carbon 2, 3, 4, and I said it's 5 carbon, right? So let's have one more over here. That's the 5th carbon. 5th carbon. Okay, that's the ribose sugar. Now, in organic chemistry, what time to draw stuff to make a point, you start, each of this corner is 1 carbon. You have to automatically assume that, and I hope you went to school, which all of you did, you should know that, especially UFC students. I don't know, who was your teacher for organic? What's her name? Vogel? No, I didn't have, I have it. Do you guys, who watches soccer? None of you guys? I don't know, there was a major German captain, Lothar Matthäus. Her cousin was my professor. Yeah. She'd always tell me a lot of stories. Okay. I guess. So technically carbon should be like this. 1, 2, 3, it has 4 bonds. And here we go. 1 is right here, 2 is here, and then the hydrogens are silent. You don't see them. But as soon as you see a corner like this is the corner, green. In the ASMLA class, they tell me don't use green because it hurts their eyes. So let me do this. This corner is 1 carbon. There's 1 bond, there's another one. The 2 that are not explicit, not visible, those are immediately hydrogens. So you assume there's 2 hydrogens attached. 1 line means 1 bond. Carbon can have 4 bonds. So in this corner, you see 2 bonds, but you don't see the other 2. And those have to be assumed as hydrogens. Hydrogens, you never write them down. All sugars are hydrocarbons. All lipids are hydrocarbons. The only difference is sugar will have oxygen in addition to that. But anyways, it's just for you to help. Nobody cares. For step 1, nobody cares. So don't spend time on it if you don't have to. So carbon 1, carbon 2, 3, 4, 5. This is sugar. And this sugar is known as ribose. Ribose, 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 ribose. What's the first letter in RNA? R stands for? Ribose. Very good. Ribose. And what's the N for? Nucleic. A for? Acid. So the nucleic acid that's found in the nucleus, and it has the ribose sugar, it's called RNA. If it has deoxyribo, DNA. And I'll come to that. Okay? All right, let's do one more thing. Now, to make it a nucleotide, we have to add what? A nitrogen base. Nitrogen base, again, these rings we have to know. Nitrogen bases comes in 2 parts. There is a group of nitrogen bases known as purine. They're purely gold. Okay? And then pyrimidines. A and G are purines. U, C, T, in that order, are pyrimidines. I want to do the order because that's how. So that means C and T are made from U. Okay. If you modify C, if you modify U, you add NH to it, becomes C. If you add to that methyl group, it becomes T. Okay. But anyhow, so this is the shape of purine. Let's compare this to pyrimidine. Now you will have them in your book. How many rings does purine have? 2. Pyrimidines, single ring. So immediately you know the difference. Now, when you get confused, think of a gold ring. G for gold, A for a gold ring. If you want a ring made of gold, would you want 2 or 1 or 2 rings, 2 diamonds? The more the better. So pure gold, you want a lot of it. So it has 2 rings, pure gold. So think pure for purine, G for guanine, and then A pure, A for adenine. A and G are pure gold. They're purines, number 1, and also they have 2 rings. Okay, just for mnemonic purpose, just to kind of like help you if you want to forget later on, because you might want to have some important information you want to put in your head rather than this later on in life. Okay. If they're nitrogen bases, why are they called nitrogen bases? They must have a lot of nitrogens, and they do. The backbone of them, the backbone. So usually they have multiple nitrogens. We don't have to memorize them as long as you know they have nitrogens in them. And for that reason, they're called nitrogen bases. Now, where do they attach to the sugar? It's from the nitrogen anyways. If this is purine, they'll attach as a 2 ring by the nitrogen. If they're pyrimidine, a single ring attached by the nitrogen, like that. Okay. So now, before attachment of this nitrogen base, it was only a ribose sugar. As soon as you attach nitrogen base, then it's called nucleoside. Nucleoside. Not nucleotide, side. Nucleoside. Nucleoside means only sugar and nitrogen base, no phosphate. The term nucleoside is used for a nucleotide without phosphate. Without a phosphate, it's called nucleoside. With a phosphate, it's called nucleotide. If they're individual, they're called individual names, right? It'd be called sugar, phosphate, nitrogen base. But as soon as you combine nitrogen base and sugar, what do you call them together? Nucleoside. If you add a phosphate in addition to that, nucleotide. Okay? Okay. Good. And I'll go over the shapes of pyrimidines and purines in a bit, but let's finish with this. Let's add a phosphate to make a nucleotide, because that's where we want to be. Phosphate or phosphorus is in the center, and it has an O, 4 oxygens attached to. Phosphorus is known as phosphate. Now what do we have? Right now we have a nucleotide. This is a nucleotide. It has 3 parts. It has a nitrogen base. Let me put N in there. Nitrogen base. And it has a sugar. And this sugar is what sugar? Ribose. And it has a phosphate. Let me color phosphate with red or orange. This is the phosphate group. This is a single nucleotide. So far we don't. Now, do you think this is a pure nucleotide or pyrimidine? Pyrimidine, good job. Because it has single ring. So the nucleotides are different based on what? On the nitrogen base. All nucleotides will have the same sugar and the same phosphate. What makes a nucleotide different from A to C to G to T to U is nitrogen base. So the easy one is first, if it has two rings attached to it, it's a purine nucleotide. It could be either A or G, right? And if it has single ring attached to it, it's one of the three, either C or T or U. Okay. Now, to know the shape of those individual nucleotides, you might get lucky and get a question, you might not. And I wouldn't spend time on it, but if you do, you want to get the 99 percentile, go for it, you know, memorize the shape. So, for example, when we think about pyrimidine, it's a single ring first of all. Oh, it's already there. Let's just do that. Pyrimidine that has two O's, one over here, one over here, that's known as uracil. Uracil. Okay. Let's write their name. So we have C, cytosine, thiamine, uracil. I'm going to remove the T because that one is a little bit unique. Let's put C and U together, and then T here. Okay. All pyrimidine nucleotides are first made in the form of uracil. Uracil is then converted to cytosine or to thiamine. So the backbone of pyrimidine is what? The precursor of all pyrimidine is uracil. Very good, uracil. Alphabetically opposite way, uracil. Now the question is, if you count 1, so 1, 2, 3, at position 4, right here, the top position, you need, let me see if I can highlight it. What color should I use so you could see? I'll use red. You see this O? I'm coloring in red. This is the region that makes a difference between C and U. In that position, if you have, so right here, this part, if you have O attached, it is uracil. And let's say you substitute this O, which is a ketone, with a nitrogen, you add an amide group, it becomes C. Look for that. As I said, in my opinion, it's not that important. You shouldn't be spending your time on that, but just in case, you know, if it sticks in your head, you never know. Okay, it'll be an additional answer. And as I said, maybe one and all of you will get that question. One of you.
What would you say that would be? What would it be if you switched it up?
C, cytosine. Now, so between C and U, what's the difference? At this position, the top position, either you have N or O. N or O, correct? Alphabetically, C comes before what? U. Alphabetically, when you say A, B, C, later on U comes, right? C is first, U is second, alphabetically, in that sense. Now, N is before what? O. Just to kind of give you some platform to work with. So C should have nitrogen attached at this position, NH2, and uracil should have O attached. Everything else should be the same. That's what makes it different. That's all. Now T, thiamine, is completely different. So it is, for example, uracil, but now you add here a methyl group, CH3. A methyl group, CH3. Here, this one in green, methyl group. Okay, so now in terms of structure, you know the difference between C, T, and U. They're all pyrimidines, but yet they're different. So what makes a nucleotide different? When would you call a nucleotide C or U or T? It's based on the nitrogen base. What makes a nucleotide different is the nitrogen base. Sugar and phosphate is always the same. Sugar and phosphate is always the same. And as a matter of fact, it's called the backbone of nucleic acid. The backbone of DNA and RNA is what? Sugar and phosphate. Sugar and phosphate. I'll show you how. So now you know the structure of a single nucleotide. A single nucleotide. A single nucleotide. Good? Similarly, if you want to work for purines, A comes before G, so A should have more O, and then G should have nitrogen. Yeah.
For the bases, isn't there two nitrogens on there or no?
Yeah, there's multiple, so there's one nitrogen here, but I don't care for it.
Okay.
It's not used in identification.
Okay.
Wow, what's going on? Here you go. This nitrogen here is not used for identification. It's the same in all of them, so it makes no difference. Yeah. Okay, so this is a nucleotide. Would you call this nucleotide ribonucleotide or deoxyribonucleotide? Ribo. Because so far we talked about this is ribose sugar. Now, you see these positions are known as prime 1, prime 2, prime 3, prime 4, prime 5. These carbons are given numbers because it's important. The sequence of this carbon is important. It will come soon. Now, at position 2, all sugars should have OHs in each of these carbon. At position 3, at position 4, 1, 2, 3, 4, 5, and all these positions, they should have OHs. All sugars. All sugars are, what's the formula of glucose? Do you remember, guys? C6, O6, and add the 2, 12. Yeah. Which means all sugar should have what? Carb, hydrogen, and oxygen. You cannot have sugar without oxygen. As soon as you remove oxygen from this, it becomes lipid. As soon as you remove oxygen, it becomes lipids. It's oxygen that makes it soluble. I can't believe I'm going to organic, but it's for you to understand. Not necessarily so. Now, the important thing is, I had to talk about this, is to tell you at position 1 you have OH, at position 2 you have OH, at position 3 you have OH, at position 4 you have OH, and position 5. All sugars in each carbon should have OH attached, because all sugars are CHO. That's a general formula. Are we good? Okay. Now, this is a ribose sugar. What if you remove an oxygen from one of these positions? You will call it deoxy. No oxygen. Deoxy. And that is position 2. At position 2, instead of having OH, DNA would have only H. It would have only H. What makes DNA? Wow. This is supposed to be a highlighter, not a painter. There you go. Even pen gives me attitude sometimes. Crazy. So at position 2, prime 2 of the ribose sugar, if there is OH, it's ribose. If it's H, it's deoxyribose. It's still sugar, it's still ribose, but without oxygen. So what would you call it? Without oxygen ribose sugar. So you call it deoxyribose. Yes, sir. Only for prime 2. The only place where DNA will have H instead of OH is prime 2 position. Everything else will stay the same. Let me just draw it for you, okay? Let me get rid of this. You guys know this by now. Now it's time to compare DNA and RNA. Let's compare DNA and RNA. In terms of structure, let's compare DNA and RNA. At the end of the day, you know DNA is made of nucleotides, so is RNA. But how are they different and how are they similar? It makes a difference for us. Why would nature or God or evolution or whatever you believe make 2 types of nucleic acid? There has to be a purpose. And if there's 2 types, they have to be different. If they're different, they have different purposes. Right? Whenever something you have too much or too many copies, That means it's for safety purposes. It doesn't have different functions. Two things that are exactly identical, they cannot have different function. They will have the same function, but when you have multiple copies of something, it's for security, for safety, so you don't lose. If you lose, you have other copies. That's the idea. Okay, so DNA. Now, again, let's do this. I'm going to draw right here. They're both made of nucleotides. They're both made of nucleotides. And both of them should have phosphate. What's the formula for phosphate, chemical formula? Okay. And they both should have a nitrogen base. So I'm trying to draw one nucleotide of DNA and one nucleotide of RNA. Look at this. What is this? That's crazy. Look at the code. Exciting. Okay. Now, let's compare DNA and RNA based on structure. Okay. See the ribose sugar? In both cases is ribose sugar, but only in DNA at position 2 only. The ribose sugar between DNA and RNA is only different on position what? 2. Everything else is the same. So that means RNA will have all OHs at all position. DNA will have OHs at all position except 2. So I'm not going to draw all of it. At position 2, RNA has what? OH group. And DNA will have H. It's deoxy, no oxygen. Deoxy. Deoxy, no oxygen. Structurally, that's a huge difference. Which means RNA is more soluble, DNA is less soluble. Oxygen is what gives it solubility. What is water made of? Hydrogen and oxygen. It's oxygen that makes water soluble, and it's hydrogen that makes the two. Oxygen is negative, hydrogen is positive, so it promotes solubility. If it wasn't for these two molecules, water will never be floating, or never be fluid, not floating. It'll never be fluid. The hydrogen bonds is what makes a difference. So anyhow, so that's one structural difference. Is in DNA, this is deoxy. The sugar is deoxyribose. In RNA, it is ribose. Done. Position 1 is normal, identical in both. Position 3 is the same, position 4 is the same, position 5. Everything is the same in terms of sugar. Phosphate in both cases is identical. So let me do this. Phosphate in all nucleotide never changes. Whether it's DNA nucleotide, RNA nucleotide, phosphate is the same phosphate. It never changes. It's the same. When it comes to DNA and then RNA, sugars in RNA is oxyribose. You don't say that. In DNA, it's deoxyribose. You do say that. Okay? Everything else in that sugar is the same. For all DNA nucleotide, the sugar is the same. All 4 DNA nucleotide, the sugar is identical. Phosphate is identical. What makes it different is the nitrogen base. Okay? But let's compare now. One additional thing. In DNA, you have thiamine. RNA don't have that. Instead of thiamine, it has what? Uracil. So now, let's do this. Let's make the differences. In terms of structure, DNA is made of nucleotide known as A, which is adenine, guanine, cytosine, right? Let me do it alphabetically. A, C, G. DNA is made of these 3 nucleotides. RNA is also made of the same nucleotide, A, C, G. But yet there is a difference, and let me use red for that. Difference. DNA has T, RNA has U. That's the major difference. Okay. RNA does not have T. Instead of T, it has what? U. DNA does not have U. Instead of U, it has T. But the other three nucleotides are the same. At the end of the day, if you look at it, DNA is only made of 4 nucleotides. RNA is only made of 4 nucleotides, not of 5. RNA is only made of 4 nucleotides. DNA is made of only 4 nucleotides. But yet there's difference between DNA and RNA. RNA has U, DNA has T. RNA does not have T, DNA does not have U. Okay? U and T, just substitute them, and you should remember. Now, if you think about it, T comes before U again. D comes before R again. DNA has to have T. RNA has to have U. Alphabetically, a lot of things make sense, just for you to remember. Okay, so that's one difference. Second difference, at position, prime to position. Prime to position. DNA has a hydrogen group. At prime to position, RNA has OH. Huge difference again.
That was just for stability.
Very good. Exactly. You want DNA to be more stable. And the double-stranded formation only. I'm coming to that next.
No, I mean like specifically at 2' and not at any other site.
Mm-hmm.
Wait, I have a question.
Yeah.
How does having things and stuff like OH make it more stable?
Hydrogen, oxygen is very electron negative. It's like a guy who drinks a lot, who parties a lot, who drives crazy, a 20-year-old, compared to a 6-year-old who has accomplished a lot and he's just relaxed. It's unstable because it has a lot of energy to give out and accept. It has more electron negativity. Hydrogen is very small, silent, relaxed in that sense. Less energy. Yeah. So it's not, for example, it's not exposed to reactions. Whereas OH can be attacked immediately. You know that in all organics, so for example, if you have a molecule that is OH, this oxygen has 2 lone pairs, and they're available for reactions. Hydrogen has only 1 lone pair, and if that's occupied right here, there's nothing available. It has nothing exposed, nothing for reaction, nothing for bonding. Oxygen has a lot of room for bonding, so they can cause problems in that sense, yeah? Okay. Again, prerequisites are good for you to understand, but it's not necessarily important for the exam. It's just understanding. So don't go into organic of it. That's not the idea. At the end of the day, this is what we want to do. Let me do 2 more things. Nina, what's your question?
No, I was just going to say, if you have OH, the fact that RNA is in cytosine, right?
Mm-hmm.
So that's why it's more soluble? Rather than
Exactly.
having it's more compacted, so you need to respond.
Yeah. And in cytosol, when you talk about transcription, I'll talk about it more. In cytosol, you don't want to keep RNA forever because they have to keep piling eventually. So you have to digest it. The OH allows enzymes to come and attack it and break it down. It's more reactive. That's why. Good. Very good. You're correct. Okay, so that's 2 differences. Difference 1, difference 2. DNA in nature, which means water, nature, is always found in double-strand formation. That's the most stable form of DNA, the double-stranded form. The form of DNA that's most stable is known as double-strand. 2 copies attached. 2 strands attached, fused together by hydrogen bonds. So DNA in nature is found in which form? Double-strand. RNA is found in single-strand. Very good, because that's the most stable form of it. Okay? And the purposes are different, and I'll tell you why. See, DNA, when it's in double-strand formation, you cannot read it. You cannot copy it. It's for protection as well. You don't want to copy those genes without any knowledge or without any execution. You know, there has to be somebody controlling those genes. For example, you guys heard of Down syndrome, right? How many copies of those genes are there? 3. You just have extra product, and look at the results. So genes have to be tightly regulated, very tightly. Very, very tightly. Because they produce your features, they produce your enzyme, they produce almost all the structures because of enzymes and proteins. So you have to regulate them very tightly. And therefore DNA, when it's closed, double-stranded, it's not available for copying. If you don't copy that instruction, you cannot make anything. RNA is single-stranded because it's supposed to be copied immediately, and after it should be destroyed. So none of this is accident. Everything has a purpose. Everything, at least in my sense. Okay, so that's one. Are there any other differences? Okay. Okay. DNA is only found in the nucleus. Only in the nucleus. Only in the nucleus. Maybe I should put only. DNA is only in the nucleus. RNA is found in the nucleolus. I'll put capital N, small n, nucleus, and cytoplasm. So RNA is found in all three locations, depending what kind of RNA we're talking about. mRNA is primarily where? In the cytoplasm, but it's made in the... So now let's talk about one more thing. DNA synthesis, the process of DNA synthesis, making new DNA copies, is known as replication. Making new copies of DNA is replication, and that happens in the nucleus. Okay, the location is where? Nucleus. RNA synthesis is also nucleus, and the process of RNA synthesis is known as transcription. Transcription, and that also occurs in the nucleus. But it's later on transported to the cytoplasm when it's processed and made. Okay, what's other difference? Well, there's one more. DNA is the original copy of your instructions or codes. DNA is the original copy. It's the original document or original molecule. RNA is a photocopy of that. RNA is a photocopy. That means, you know, you can afford to throw a photocopy in a garbage, shred it, whatever you want once you're done with. Original copy, you can't do that. Especially if the original copy is, you know, you go to a country and then you get a new passport and citizenship, and that's your identity for now, and there's nothing else. Donald Trump will like that, right? And then, you know, you don't want to lose that. So DNA is the original copy. Thank you, Ahmed. The original copy. mRNA is the photocopy of that. Photocopy of that. Okay? Not all RNAs, just mRNA. Last thing, so we're done with what is the difference between DNA and RNA. Okay, we know now a little bit difference. There's a difference between DNA and RNA. Okay, good. Now, DNA can come in different forms. For example, it can be called bDNA, cDNA, and aDNA. bDNA is the most appropriate one. cDNA means copied. Usually it's saved just if you have, for example, you have C in front of DNA. In terms of structure, there's no difference. All DNA is the same. But cDNA is, for example, usually copied and stored where? In laboratory and things like that, just for sake of, or something you can refer to complementary DNA. Okay, so that's for that. Now, let's compare three DNAs in terms of structure. zDNA, I don't know if this will be important, but let's go over it. And bDNA. And I think there's aDNA as well. Check in your book, the first page of... I think there's aDNA as well, but let me just write it down. These are based on types. Go more. There you go.
Yeah, A, B, C, and Z.
Okay. So C is not necessarily based on the look of it. It is simply called either, sometimes it refers to circular DNA, complementary DNA, or copied DNA. Okay, that's just for copied DNA in a sense. Multiple copies are stored so they can be used for identification, things like that. Circular DNA is only for viral or mitochondrial. You did the question today, good job. And then complementary DNA means a single strand is opposite of the other strand, or exact identical copy in a sense. Okay. Z-DNA, Z stands for zigzag, zigzag, zigzag. B-DNA stands for right-handed DNA. And A-DNA, left-handed DNA, for example. And now zigzag DNA, so DNA, I wish I had two pens at the same time. Oh, I can do that, right? Let's see if this will work. No. I'm trying. How do I do double helix? I'll try without it, okay. So DNA is twisted and it's a helical form. Have you guys seen those springs that you can stretch and they collapse? If you stretch it, that's what DNA looks like. If the stretch is longer, larger, it's bDNA. If the stretch is shorter, it's aDNA. And that's important, I'll tell you. Okay? So let me draw something for you. Like, let's say this is the DNA. Now all DNA is a double helix, right? Why is it called double? It's two strands attached together. For example, if I take this wire, single wire, now I have two good. This is double-stranded. There's one strand, there's two strands, but they're not separate, they're not free, they're attached. They're attached, they're paired. And this pairing up is done because of hydrogen bonds. Okay, now let's say the nucleotide will make this hydrogen bond, so you see something like this, like a ladder. Did you guys know that they were supposed to make a DNA building, shape of DNA building in downtown Chicago? It was approved because the economy didn't proceed with it. There's supposed to be a building exactly the shape of DNA. Because Chicago is known as the center of, San Diego and Chicago is known as the center of medicine.
Really?
Yeah. Yeah. Yeah.
You didn't mention that DNA is negatively charged.
I'll mention it. He's right. The phosphate group, phosphate is 4, oxygen is 2 negative charges. Always negative. DNA is always negative. That's very important. And as I said before, I think we mentioned this in the cell, right? When you say inside of the cell is what? Negative.
Is the RNA
Yeah.
also negative by that?
All nucleic acid is negative because of phosphate. And the oxygen of sugars makes it negative. Overall. Okay, the overall charge of this molecule is negative. Okay, if this is DNA, now look at these twists. The twist here, one of the twists, and it keeps alternating. This twist is larger. This is known as major groove. Okay, and then look at this twist. It's smaller. Smaller groove. If something is twisted like this, tighter, that means you have enzymes that should copy this DNA and open it. To be copied before you have copy, you have to open it into single strands. They can't get in there physically. So a DNA whose grooves are smaller is usually A or Z DNA. They're transcriptionally inactive, replication-wise inactive. You cannot transcribe them or replicate them. Transcription more than replication, meaning they're not useful for what? For protein production or enzyme production. They're transcriptionally inactive.
The large one's bDNA? The large one's bDNA?
Yeah. Both will have, look, all DNA will have the smaller groove and the larger groove. Does it make sense? All DNA have them. But in A DNA, they're more compressed. The large and the small groove are even smaller. I wish I had a spring. So think about it this way, look. This is bDNA. This is aDNA. And zDNA looks zigzag. It's not smooth. It's like rough. So zDNA will look like this. Uh-oh. It is spiral, but it's rough spiral, like this. It's called zDNA because it's zigzag in shape. It's rough. It's transcriptionally inactive. Let's just put this. Inactive. Inactive. Okay, bDNA is mostly what we need. In the twist of the helix, in bDNA is right-handed. Right-handed. The twist is right-handed. In aDNA, it's left-handed. And again, that plays a role somehow because its stability increases or decreases. As a result, as long as you know, just recognize, I mean, it could be good for your knowledge, you can show off with it, but you need to know only two things: the difference between them and which one is more active, which one is less active. B DNA is the best DNA. B for best.
It's the active form.
Okay. Okay, so that's for this. So look, we have four types of DNA, but they're all the same. It's slightly different in structure. In terms of function, some is active, some not active. When it comes to RNA, there are different types of RNA. Yes, sir. If I ask you to please speak up, would that be okay? Because the AC is really, I can't hear you good. Yeah. Yeah. Yeah, for all DNA, the grooves are small, large, small, large, small, large. But in B DNA, the grooves, the major groove is stretched more. In A DNA, it's more compressed. There's less room for enzymes to get in there and open them. When it comes to replication, I'll tell you how the DNA is open, how it's copied, and stuff like that, okay? It'll make more sense. But for now, we just have to learn based on shape. You know, with knowledge, it's difficult to give you everything at once. You know, I'm trying to do it in a stepwise fashion so you can have at least the basic knowledge and you can have complicated issue later on. Yeah.
Is left-handed more stable
Yeah.
because it's compacted?
Very good. Okay. Now, when it comes to RNA, there are different types of RNA, then we'll take a break. When did we start? 44, right? 8:44? 45, okay. RNA, you have tRNA. You have mRNA. And you have rRNA. Three types of RNAs. T stands for transfer. Transfer or transport. You don't like transfer? Say transport. M stands for messenger. Messenger. R for ribosome. Ribosomal RNA, messenger RNA, transfer RNA. Three types of RNAs. Three types of RNAs. Good. Now, in terms of shape, tRNA looks like a T, believe it or not. It looks like a T. I'll try to make it like a T then. Wow, what's with my circles? Okay, it's fine. There you go. Looks like a T, right? Kinda. You can relate to this T. Okay. Looks more like a cross, but T. I just want to make some correlation. In this shape, you should memorize because this might come on the exam. This is not something you're unlikely to see. This is very likely to see. You would see this. So, okay. Now, when it comes to tRNA, it has three circles, right? You see that? So let's say now this tRNA is actually paired. So when I say the blue, these are hydrogen bonds. They are paired. You see the circle is open. Three circles. This is one loop. So let's call this a loop. This is another loop. And this is a third loop. So tRNA must have how many loops? Three. I just remember something. Was it is there a four corner thing in New York or something? One of those gangster movies I was watching, they have those 5 loops or whatever. They're fighting 5 families, whatever. I don't know why things come to. Every time I see Mazan, I think of movies because he doesn't like movies. Okay, loops. Now, the only loop you care for is the second one, the bottom one. This loop will have something called codon. Codon. If you can just memorize and be patient with me, I'll tell you soon what it is.
Is it the codon or the
Anticodon. Very good. There you go. Anticodon. And anticodon is only 3 nucleotide in length. It never changes. It's only 3 nucleotide in length. Anticodon. Look what I'm telling you. You know, it seems very simple, but you're gonna forget because you think it's too easy and you think this could not be relevant. It's very relevant. Anticodon is only 3 nucleotide in length. Not longer, not shorter. Exactly 3. Give me a sequence of one of those nucleotides. AUG. Give me another one. Give me another one. What nucleotide does not belong in this? T. Never choose T because this is RNA. Okay, good. Now, this tRNA has the 3' end and the 5' end. Okay, so, oh, I should have said that. Okay. Do you remember when you talk about a nucleotide? So at least you can translate it here. When you talk about a nucleotide, the carbons were 1, 2, 3, 4, 5. The sugar and phosphate is the backbone. Okay, and the sugar and phosphate only attaches 5 to 3, 5 to 3, 5 to 3. Let me show you. For now, just memorize. Let me finish this and I'll show you soon. Let me finish this because I don't want to confuse you. Now, the 3' end will have A, C, C as a nucleotide sequence. This is conserved in nature. What does A stand for? Adenine. C for? Cytosine. C for? So look what it tells you. ACC. If you were to put here at the end E, P, and T, how would you pronounce that? ACC, EPT. Except, this is the acceptor site. I don't know how it worked out. It's just crazy. Sometimes, I don't know, like, scientists do things by mistake and then things work out. It's crazy. It's a transfer RNA, right? It transports something. What does it transport? Amino acids. Amino acids. Amino acids. The 5' end will have OH. It's blocked. Okay. So now, the 3' end has the acceptor site. Guess what? What does it accept? Amino acid. Amino acid. This is where it will attach or bind. Let's say amino acid is in green. This is, excuse me. This is where it will attach amino acid. I'll put AA, amino acid. It binds amino acid. It's a seed for amino acid. That's where amino acid will attach. Where? At the 3' end. ACC, acceptor site. It accepts amino acid, brings it to the ribosomes, and then we do the rest later. For now, just identify structure of tRNA. It looks like a T. It has 3 loops. The second loop, the middle loop, the bottom loop is the anticodon. The other 2 loops are for stability. You know, like when, did you guys know that in Chicago, like last summer, there was a guy walk from one building to another building on a rope? For him to walk, he has to carry something like this for stability. That's what the tRNA has, the 2, the first and third loop for stability. So it can move and it can fit exactly in the garage called the ribosomes. It will park there and it will donate its amino acid. And I'll tell you that's protein synthesis. For now, as long as you can tell me the structure of tRNA. There are 3 locations very important. The second loop, where you have the anticodon. The anticodon is only in one location, nowhere else. Also, anticodon is only 3 nucleotide in length. Anticodon will never have a T. Will have A, C, G, or U. Never T. Okay? All right. So that's tRNA. And what's the function of tRNA? To bring amino acid ribosomes into the ribosome. So it transports. It's a taxi. It's a cab. It's Uber. Whatever. Train. Does not matter. Bicycle in the snow. A bicycle would more look like a tRNA. Has, you know. So tRNA simply brings amino acid, carries amino acid, transports amino acid. Okay. So that's tRNA. We're done with tRNA.
So it brings amino acids into the cell?
Into the ribosomes. To the ribosomes. Okay. When I talk about protein synthesis, all of this will come into play. But right now, I only care for what does tRNA look like? What is its function? That's all. Two things, structure and function. What is it involved with? We'll go in the process. It will give you more detail after the break. So let me just do last thing. mRNA is messenger mRNA. M stands for messenger mRNA. This is the mRNA that's actually used as a code to make a protein. So that's messenger mRNA. And the shape of this mRNA is always linear. Linear. A straight sequence of nucleotide. And the sequence is extremely important. Yeah. One of you, if you had a slight mutation in this mRNA, you might have looked like me. And you don't want to be like me, right? So, and I don't want to look like you. If I had a mutation, it might have, these are the things that happens. The sequence of nucleotide, extremely important, extremely. Okay, ribosomal RNA is the most abundant RNA in terms of percentage, the most abundant RNA of your cell. Ribosomal RNA participates in ribosomal synthesis. So the ribosomes, this thing that we studied before, ribosomes. How many types of ribosomes did you have? 2. What are they? Free and attached. Okay, that was in terms of function. How about in terms of structure? 2. Large and small subunit. Large was 60S and small was 40S. This is only in humans or eukaryotic cells. In bacteria, it's different. Okay, it's 50 and 30 in bacteria. But anyhow, the ribosome is made of 2 things: ribosomal RNA and plus proteins. That's what makes ribosomes. So the ribosomal RNA is for that purpose. Make sense? Messenger, carrying message. T, transporting. Ribosomal RNA is involved in protein synthesis. Protein synthesis. Protein synthesis. Shape is irrelevant, yeah. Globular, if you would. Yeah. So you will have a huge protein like this. Let's say in red, there's a RNA within it. Okay. Very good, very good. So at least we know what are the types of RNA, what are their shapes, what are their functions. So thank you, Muhammad. Let's just please, even though I said it's irrelevant, but no, it's globular. It's never fibrous. Ribosomes are globular protein. What does globe mean? Round. Globular protein means what? Round. Fibers are long, thread-like, hair-like. And hair-like structure are insoluble. Globular things are soluble. And you want your proteins to be soluble in water, otherwise they won't be able to do anything. Structural things should be fibrous. Functional things should be able to move around and swim. Globular. Globe is actually swimming in water too, right? Okay, let's take a break, and then we'll come back.